Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So next speaker is Kush Bhatia. He is currently a research fellow with MSR India, and before that he did his BTech from IIT Delhi, where he got Director's Gold Medal or President's Gold Medal, sorry, Silver Medal. And yeah, so he will also talk about extreme multi-label classification.
Okay, hello everyone. I'm going to talk about our algorithm X1 for the same extreme multi-label classification problem as Yash talked about. So as Yash had already explained, but just let me go over this briefly. There are various kinds of classification problems which arise in the in the machine learning literature. The most common one is the binary classification problem, where you're given two choices and you need to select one of them. So, for example, in the US elections, you can either vote for the Democrats or the Republicans. A generalization of that problem is the multi-class classification problem. For example, in the Indian elections, you're given more than two choices, and as a voter, you can vote for one of the political parties that contest elections. An even more general problem is the multi-label classification problem, where you're given three choices, and instead of selecting one, you need to select all those which are applicable. So, for example, in this tagging the celebrity task, if you consider all the people on this earth to be your set of categories, you need to identify the correct people who are there in this photo. So, this is an example of the multi-label classification problem. And as Yash had already mentioned, this also comes up very frequently in document tagging tasks. For example, this is the Wikipedia page for Bharatnatyam, and you need to tag it with the relevant categories or tags. So what makes this problem difficult and interesting at the same time is that you have around 500,000 labels present, and you need to select only 5 or 6 which are most relevant to your document. So this makes the problem both interesting and difficult to solve. Let's try and formulate this problem mathematically. So if you let X represent the space in which all your documents lie, and Y represent the discrete space of labels, the objective in extreme multi-label classification is to learn this function f, which when presented with a document, it identifies the correct subset of labels which are relevant to your document. And there's been a whole lot of research done in this area, and the kind of techniques that are available in the literature can be divided into 3 broad categories. The first one is the one versus all or binary relevance, which assumes the label to be independent. The second class of techniques are these tree-based techniques, which Yash talked about. And the third class of techniques is the embedding based techniques, which we'll focus more on in this talk. So let's just go over them one by one briefly. So in the one versus all or binary relevance technique, you assume all the labels to be independent, and you learn functions separately for each of the labels. So when you have a new document, what you do is you pass them through each of these functions, and each function predicts a score for the document. This score tells you how relevant that label is to this document, and the final predictions are made by thresholding these score values. So there are some problems with this method for our extreme multi-label classification problem. So the thing is, even if you assume these f to be linear classifiers, the storage space comes out to be order LD, because you need to store a classifier for each label. And in the setting for Wikipedia, where you have a million labels and more than 100k documents, the storage space comes out to be 300 GB, which it makes it practically infeasible for such large scale classification tasks. Also, the test time is L times D hat. So let me just go over this notation once. D hat is the average number of features which are active per document. For example, if you see the Wikipedia dataset as a bag of words representation, the number of words which are important in each document are typically very less as compared to the total number of words in your vocabulary. So in the wiki LSHTC dataset, which even Yash mentioned about, DHAT is typically 50, while the whole dimensionality of the dataset can be as large as 1.6 million. The next set of techniques is what Yash talked about. They are the tree-based techniques. So each leaf node in a tree has a distribution over the labels, and when you're presented with a new document, you pass it down to. So this is a forest of trees, and when you're presented with a new document, you pass it down to through each of the trees. At each leaf node, you get some distribution over the labels. You aggregate those distributions, and you make the final prediction for this document. So this is in general how tree-based techniques work. And we are interested in these embedding-based approaches. So as you can see, the document lies in a very high dimensional, albeit sparse space, and the label vector lies in a very large L-dimensional binary space. The key idea in these embedding-based approaches is to project both of these onto a very low-dimensional, k-dimensional space. So the key task is to learn these transformations W and H so as to transform both of these to a common space and then do prediction somehow. Most of the different embedding based methods actually differ in the way they learn these transformations W and H. So what are the key advantages that this method has over some other methods? So typically this rank of the subspace on which you are projecting is much less than L or D. So where L and D can be of the order of millions, this case typically a few hundreds. The storage space comes down by a factor of L or D because it's now only L plus D times K, and the prediction time is L plus D hat times K. So if you see this carefully, if K is greater than D hat, the prediction time is actually worse than what's there for one versus all techniques. So this is something we would like to address in this talk as well. So let's have a comparison of the tree and embedding based methods. Both of them have their own advantages and disadvantages. So FastXML is like the state of the art tree based method, and LEML is the state of the art embedding based methods. As you can see, in terms of prediction time and precision, the tree based methods typically outperform the embedding based methods by a huge margin. However, when it comes to model size, these tree based methods tend to have a very large memory imprint when you compare it with embedding based methods. Just in summary, we want to work on these 4 parameters: accuracy, prediction time, model size, and theoretical understanding of these algorithms. So typically tree based methods do very well on accuracy and prediction time. However, in terms of model size and theoretical understanding, not much is known about them. So even for the state of the art methods, you don't have consistency guarantees. Whereas for the embedding based methods, although they tend to perform poorly in terms of accuracy and prediction, they are very well understood theoretically, and they have reasonable model sizes which you can work. We want to propose an algorithm X1 which does well on all these parameters. So that's something that's going to be like our objective going forward in this talk. Since you're going to basically work in this embedding space, we should take some time to understand why these embedding based approaches don't have a good accuracy on such large scale performances. So this second plot that you see here is actually a label histogram of the wiki LSHTC dataset. So what it shows is on the x axis you have the labels, and on the y axis you have the number of documents in which those labels are. Note that the y axis is in the logarithmic scale, and you can see there are hundreds of thousands of documents which occur in less than 5 documents, hundreds of thousands of labels which occur in less than 5 documents. This presents this distribution a very heavy tail distribution, and in the presence of such heavy tail distributions, it's not reasonable to be able to capture this distribution through a low rank subspace, and this can be verified empirically as well. So if you see the blue line in this plot, what this is trying to capture is if you try to have a low rank, if you try to project the label matrix onto a low rank space using even a rank 500 approximation, you can capture only 10% of that matrix. However, if you look at this red line, this is the local SVD line. What this does is it tries to it tries to cluster the documents into different regions and tries to fit a low rank subspace into each of those clusters. So one of the key insights that you get from here is that this label distribution is not low rank in its entirety, but if you start looking at local clusters of labels, you can approximate this very well with the help of a low rank approximation. So the data is locally low rank and not globally low rank, as these embedding methods have been trying to assume. This is just a recap of our objective slide. So we want good accuracy, prediction times, model sizes, and our algorithm should have some theoretical basis to it. This is our objective going forward, developing our algorithm X1. So let us just spend some time on what was the key insight that we had from that from 2 slides back. In the presence of such a heavy tail distribution, k nearest neighbor algorithm is known to be a consistent algorithm in such settings. So basically what you can expect is the k nearest algorithm to give you good results. However, in our large scale setting, this is practically infeasible because the test time is order n times d hat. So even if you have like a million documents, you're going to spend a lot of time going to each document and seeing whether it's your nearest neighbor or not. Since k nearest neighbor is a consistent algorithm in such a case, what we would like to do is we would like to design an efficient and accurate method to perform nearest neighbor search basically. And our solution would be now to have low rank embeddings which preserve this neighborhood. Let's delve into our solution now. So all the embedding methods that exist in the literature till now can be classified under the broad umbrella term of linear embeddings. What they're implicitly trying to do is, if you have these documents in the original space and these are the embeddings for those documents, so what they want to do is this is the objective function that they try to capture. They want to say that the distance in the embedding space should well approximate the distance in the original space, and they try to model it for all pairs of documents. So it doesn't matter for them if the document is close or far, they would want that distance to be well approximated in the embedded space. However, if our main objective is to actually do nearest neighbor search, what we care about is our neighborhood and not distance in the documents in the neighborhood, and not to every other document. So what we propose is a locally nonlinear embedding method which tries to preserve for each document distances to only those documents which are in its neighborhood in the original space. And if we just try to formulate this mathematically, you want to minimize for each document. For each document, you want to minimize the difference between the distance that's there in the embedded space and that's there in the original space. This turns out to be an instance of the low ranks matrix completion problem, and we solve it using the projected gradient descent method, also called SVP. So this is how we obtain our embeddings using the label vectors. We solve this objective function using the projected gradient descent methods. So right now what we have is you're given a label vector, you have to get the embeddings. All you need to do is you run that projected gradient descent method, and to go back to the label vector from these embeddings, all you need to do is a nearest neighbor search. What remains to be done is to learn a way to predict these embeddings using the feature vector of the documents, because when you have a new test document which comes, you would ideally want to predict its embeddings and then go to the label vector from there. So this is the formulation that we propose for learning these regressors W. So I'll go over briefly what each term means in this objective function. So we want to learn regressors W using X, which can predict these embeddings very well. So this is the standard least squares loss function. You don't want this regressor to overfit to this data, so you put a Frobenius norm regularizer. And finally, there is an L1 regularizer over XW. So we are going to use XW as our embeddings for the training data, and we want those embeddings to be sparse. L1 promotes such sparsity, and that's why we put an L1 regularizer over there. We use the ADMM approach of Spreckmann et al. To solve for this W. So that was our algorithm X1 in a brief nutshell, and now let's see what happens when you have a new point coming in. So you use the W that you used, the W that you learned to obtain these embeddings. You embed this in this low dimensional space. You do nearest neighbor search in this low dimensional space, and you obtain your label vector. However, for this large scale implementation, what happens is the test time it comes down from n d hat to nk, but it's still very high. It's linear in n, and you don't want your test time to go linearly with n, d, or l, because all of them can scale to millions. And also, if you try to approximate this whole structure, whole global structure using a low rank subspace, the dimensionality of that low rank of that subspace can be very high. So what we propose in this large scale implementation is a divide and conquer approach, where you cluster the data, initial data that you have in the feature space, and in each partition you separately learn a regressor and embeddings separately for each of these clusters. Now, as soon as you talk about clustering in such high dimensional spaces, the curse of dimensionality starts to follow you, and because clustering in such high dimensional spaces can often be unstable. So in order to avoid this curse of dimensionality, instead of learning a single X1 learner, what you do is you learn an ensemble of X1 learners. And these ensembles differ in the way you seed your initial clustering. So X1 would differ from X1 any in the way the initial clusters are initialized, and how it would go on. Now what happens if you are presented with this new test document and you have such an ensemble of learners? So the test document is passed on to each of these X1 learners, and inside each X1 learner you have a clustering of the initial data. You figure out the exact partition in which this test document lies. You embed that using the regressor, the local regressor that you had learned for that partition. You embed it into the low dimensional space. You do nearest neighbor, and finally you get the predicted label using this learner. You do this for all the learners that you had learned, and finally what you have is a label prediction from each of the learners. So you aggregate those label predictions and you make your final prediction in terms of this ensemble method. Aggregating labels. So let's say one of the ensemble tells you that it thinks that label 1 and 2 are active, and the last one tells you that labels 1 and 4 are active, and the scores for all these labels are very high. So you would want to predict 1, 2, and 4, all these labels together. So let's go over some nice properties that our algorithm X1 has. The prediction time is independent of n, d, and l, all of which can go up to millions. It's only dependent on this quantity nc. This quantity nc is the number of points that you have in each cluster, and appropriately using clustering techniques you can control that number. We have final sample consistency guarantees for X1, wherein we guarantee that even if a new test point comes, the embeddings would indeed preserve its in population neighbors. In terms of storage, all you need to store are the embeddings for each clusters and the sparse predictors. The only thing that needs to be done is to check how it performs as an algorithm when compared with these other baselines. So again, we did an extensive experimental evaluation over a variety of low, medium, and large scale data sets, where the label cardinality varied from 100 to 1 million labels. All of these are publicly available except for this ads 1 million dataset, which is a proprietary Microsoft dataset. So I'll go over the results one by one from the medium scale and small scale datasets to the large scale datasets. So let's compare X1 with other nearest neighbor baselines that we have. So Wasabi is is an embedding based method which does nearest neighbor in the embedding space. It's very similar to our method, but it differs in the way it learns its embeddings. And KNN is the vanilla nearest neighbor classifier that's present. And as you can see, it's almost we have almost a 10% improvement over these KNN and Wasabi based methods on BibTeX, and another data is Uralex. We perform consistently better than both of them. Comparing this with state of the art embedding based methods, so LEML is the state of the art embedding based method, And I've put in 1 versus all classifier here as well for comparison purposes. As you can see again, there's a huge margin between our method and these existing baseline methods. The third category of methods which Yash presented, FastXML, even in this regard, our algorithm X1 is doing much better than any of these existing methods. So on small and medium scale datasets, on all the existing categories of methods, our method is able to perform the best. Let's move on to some large scale results. So I've shown results for 3 datasets: Wiki, LSHTC, Delicious Large, and ADS 1 million. Most of the methods were not able to scale to such large scale, the KNN, 1 versus all, and Wasabi. So I've put in only numbers for X1, FastXML, LPSR, and LEML. Even LEML was not able to scale very well to the ADS 1 million dataset. And as you can see, in terms of large scale datasets, we have a 30% improvement over the best embedding based methods that are out there. And even in terms of the tree based method, we have a 7% improvement. So consistently we are doing better in terms of small, medium, or large scale datasets in terms of precision accuracy. What happens in terms of prediction time? So the state of the art embedding based method LEML takes around 280 milliseconds per test point to predict, whereas we take around 8 milliseconds, so that's an order of magnitude improvement. As compared with tree based methods, we are still far off, and this is something we would like to work on in the future. Comparing model sizes, so both X1 and FastXML are ensemble methods, and so we vary the number of learners in the ensemble, and we plot the precision accuracy versus the model size. As you can see, to beat 50 FastXML learners at 10 GB, we require only 2 X1 learners at around 1 GB, and over there only a single X1 learner is sufficient to beat around 50 learners of FastXML. So in terms of even model sizes, we are doing much better. Just to summarize what I have presented, so extreme multi-label learning it's a very important machine learning problem where there are 3 broad methods: nearest neighbor, embedding, and tree based. In situations where I showed where the label space has a heavy tail distribution, KNN is possibly the best method. However, it does not scale very well to large scale methods, and we presented our algorithm X1, which is a nonlinear embedding which preserves only local distances rather than preserving all pairwise distances, and we showed like state of the art accuracies with moderate model sizes, prediction times, and proved theoretical guarantees for the same. I would like to thank my collaborators Himanshu, Purushottam, Pratik, and Manik, who helped me and worked with me on this.
Any questions?